This video is on quantities of heat. So there's two major equations we can use looking at factors of heat and their quantity. We can either use our calorimetry equation, where we have changes in temperatures, and we use our equation of delta H is equal to Q, which is mc delta T, so mass times specific heat times change of temperature. Or we can look at the heat of a phase change, where our item is actually changing phases, and that has the equation of Q equals mH vap, or Q equals mH fusion. And here we have Q's the same, mass for each one, but then we have differences in specific heat times change of temperature, and here H vap and H fusions are heats of those phase changes. So let's identify our variables first. Q is the heat lost or gained. And that's measured in joules, which is capital J. Okay. M is going to be our mass, and that's in grams. And that's the same about both of them. But then we come to our differences. Our calorimetry problems have C, which is specific heat. And specific heat is the amount of heat required to raise 1 gram 1 degree Celsius. It has units of joules per gram degree Celsius. In other words, the amount of energy required to raise 1 gram 1 degree Celsius. And you can see that in our units of energy per gram degree Celsius. Delta T is equal to T final minus T initial. So our final temperature minus our initial temperature, and that's our change. And that's going to be in degrees Celsius. Notice that I have joules, degrees Celsius, and grams, just like my units in my specific heat problem. Here I have heat of vaporization and heat of fusion. And these are the energy required for the phase change. These are going to be different depending on what item we use, but we're going to focus on water. For water, your heat of vaporization is 2,260 joules per gram, and the heat of fusion is 334 joules per gram. For our calorimetry problems, we're going to look at our specific heat. That is going to be different for all 3 phases of water and for any metal we're using. For the 3 phases of water, these are found on your reference guide, as are your heat of vaporization, heat of fusion. Specific heat of liquid water is 4.18 joules per gram degree Celsius. Ice is 2.05 joules per gram degree Celsius. And steam is 2.02 joules per gram degree Celsius. And like I said, all metals will have different ones as well, and they're also listed on your reference guides. These two equations are used at different times. Our calorimetry equation is going to be used when we have a change in temperature, or when a metal is placed in water. Our heat of phase change problem is going to be used when we have no change in temperature or when we are at a phase change. For both of these, we can have positive Q's or negative Q's. In other words, heat lost or gained. A positive Q is heat gained, and that's going to be endothermic. And negative Q is heat lost, and that's exothermic. Looking at a heating curve, where can we place our two equations? We have our first equation of Q equals mc delta T, or we have our equation of phase change, which is Q equals mH of either fusion or vaporization. This being a heating curve of water, we have our position 1 where we're heating, 2 we're at a phase change, 3 is heating, 4 a phase change, and 5 is heating again. Anytime where we have changes in temperature, we are going to use our equation Q equals mc delta T. And our C is going to change depending on what phase we're in. At our coldest temperature below 0, we have ice. Then between 0 and 100, we have our liquid water. And between 100 and above, we have steam. When we're not increasing or decreasing in temperature, and we are at our phase changes, we're going to use our equation Q equals mH. And our H value is going to be dependent on the phase change. Going from a solid to liquid, we're going to use our heat of phase change of fusion, which is the 334 joules per gram, and the heat of vaporization between liquid and gas, and that's your 2,260 joules per gram.